Hey guys, Mike here from ArnoldTutoring.com with a solid integration question. So let's take a look at how we solve this. We have the integral from 0 to pi over 4. Remember, these are our limits here. So it tells us how far along the x-axis we want to find the area under this curve. And again, in this course, as far as we're going, we only need to solve integration by what I'll call sort of the backing into technique. And all that means is there isn't any special substitution or anything we need to do. We just need to think about what the derivatives of certain functions are so that we can find the antiderivatives. So really when we go to solve integration, we're just taking the antiderivative of each piece within the integral. So the first piece is this 4 ln 2 times 16 to the x. What is the antiderivative of that? Well, first of all, we want to notice that 4 ln 2 is just the constant in front of the term with the x. Constant multipliers, we know, don't affect derivatives or antiderivatives, so I'm just going to write that out front. So we're solving the integral here, equals. So 4 ln 2 just comes along, and I only have to worry about the 16 to the x. Let's try and think about what the derivative of 16 to the x is. Well, I know the derivative is you just rewrite the term times ln of the base. So ln of 16. So if that's the derivative, taking the antiderivative of 16 to the x must be 16 to the x. And then I'm going to divide by ln of 16. Let's think about that. Why is this correct? Because if I take the derivative of this piece, I'll get 16 to the x times ln of 16 divided by ln of 16, and that's what will cancel it out. So antiderivatives, you just do the opposite of the derivative. Here, 16 to the x is multiplied by ln 16 as the derivative, and when this is the normal function. So if we are starting at just this piece, then I need to divide by ln of 16 to get back to 16 to the x. Okay, so that takes care of the first term. Now we look at plus 3 secant squared x. Where have you seen secant squared x? Well, that is the derivative of tan x. So this one's pretty simple. It's just plus 3 tan x. And we're going to evaluate, I'll put the x in a bracket, we're going to evaluate this, so that's why the vertical line, to evaluate it from 0 to pi by 4. Now, when we evaluate, that just means we place the top value in for x wherever we see it, and we place the bottom value in for x wherever we see it, and we subtract the two. But first, I'm actually going to simplify, because hopefully, and often in these questions, they're setting you up so you can simplify a little bit. Let's remember our logarithm rules. This 4 ln 2, when we have a constant in front of a logarithm, that can also be placed as an exponent on the term inside. So that is just ln of 2 to the 4. Times 16 to the x all over ln of 16 plus 3 tan x from 0 to pi over 4. Now if we look, ln of 2 to the 4, that's just 16. Ln of 16 over ln of 16 can just cancel. So the simplified integral, or antiderivative I should say, is this. So that looks a little bit nicer. Now let's plug in our values. So we have 16 to the pi over 4 plus 3 tan pi over 4 minus, and be careful, make sure you put a big bracket after the minus so that we don't miss any signs, 16 to the 0. I'm now plugging in the bottom limit, plus 3 tan 0. Great. What does this equal? 16 to the pi over 4. We're just going to leave that as is. We'll just, because that's just a perfect constant. We don't want to really plug that into the calculator because it won't come out with anything very nice. 3 tan pi over 4. Well, tan of pi over 4 is 1. So this is just plus 3 times 1. Minus 16 to the 0 is 1. Anything to the 0 is 1. Plus 3 tan 0, that's plus 3 tan of 0 is 0. So this all comes out to 16 to the pi over 4 plus 3 minus 1, so it's plus 2. And this would be an exact value to leave it in when we don't have a calculator. So again, it's just working through antiderivatives. The best part about solving integrals is that we can always check our answer. We're very good at finding the derivative of any function. So once we think we found the correct antiderivative right here, I would just take the derivative of this to make sure you get back to what was inside the integral. And if you've done that, you know you've integrated properly. Then plug in your limits and subtract. Hopefully this is helpful. We'll look at a lot more integrals as well. You can find them on our YouTube page, and you can always send in more questions at info@arnoldtutoring.com. Thanks.